Welcome. Today's lesson is entitled Rational Exponents. The good news with this particular lesson is that it overlaps with a lot of content that we've seen before. However, we will go ahead and try to simplify some pretty complicated algebraic expressions over this lesson. So it does get a little harder as we go through the process. But in the meantime, I guess just a very quick explanation. What does it mean to be a rational exponent? And then we'll jump into the investigation. A rational exponent really just means fractional exponent. So you can even see these within the investigation: 5 raised to the 1/2 power, 12 raised to the 1/3 power, 3 raised to the 7/4 power, 10 raised to the 2/3 power. So as you can see, just fractional exponents. And what we're going to do in this particular investigation is just see the connection between these fractional exponents and roots. So it's as basic as it gets. We're just going to write yes or no there and just draw a conclusion. Is 5 raised to the 1/2 power the same as square root of 5? And is 12 raised to the 1/3 power, equal to cube root of 12? So let's go ahead and just give it a try. We'll just do a little typing and then throw it in there. So grab your calculator when you do get a chance. I'm going to bring this on over here. And I think I'll just do both simultaneously, and then we'll throw in our yes or no when we get an opportunity. So 5 raised to the 1/2. Here we go. So 5 raised. I have to do parentheses on mine. So something like that, 5 raised to the 1/2. And I get about 2.23 and change there. And then what I'm going to do, of course, is the square root of 5. And you can see that right here. So I hit second, and then that, and so square root of 5. And you see, of course, I do get the same number. So there we have an equivalency. 5 raised to the 1/2 is the same as the square root of 5. How about the 12 there, base 12? I saw that raised to the 1/3. So same idea. Let's throw that into the mix. Looks awesome. And cube root of 12. So in this case, I'm not sure if you've seen cube root on the calculator, but it'll be under the math menu. So go ahead and hit math for me. And you can see it's about the 4th one down there. So do whatever you need to do, but get that cube root. And cube root of 12, same number, of course. All right, perfect. So we are ready for our first conclusion. So first and foremost, big fat yes in there. Same in there, looking good. And our conclusion number 1, here's what I have on my sheet. So when we have a base raised to the 1 over n, so in this case, the nth root is what it's going to be equivalent to. And so that's, I think, what we would formulate. So in this particular case, if the 2 is the denominator of our fractional exponent, that is the root of the base here. So in this case, the second root, or square root of 5. And obviously, as we saw here, so the 3 is in the denominator, and so that would be the cube root as a result. So the denominator looks to be equivalent to the root of that base. Awesome. Let's go ahead and jump into C and D. Same idea, just throwing it in. So I'll do 10. Now raised to the 2/3. So really the only difference between these two parts of the investigation would be that the numerator of the fraction is not 1. So 10 raised to the 2/3 sounds good. Let's see if we can get an equivalency with that. And it looks like on your sheet we have another cube root going on. So I'm going to go under the math menu again and go cube root right there and cube root of 10 squared. And as you do notice, we do get the same value. So kind of keep a conclusion in the back of your mind before I even write it. But let's go ahead and just confirm what we're seeing here. So 3 raised 7/4. Very nice. Got it. And then what does that mean in terms of its equivalency in what we would call radical form? So using a radical. Well, I'm going to go ahead and try to do the 4th root on my calculator. And if you haven't seen this before, for my particular calculator, you have to hit the number 4 first. And then same idea, it goes under the math menu. And it's right there. So it's the x root. So I already told the calculator that I needed the 4th root. But now I go right there. So the 4th root of 3, and then raised to the 7th. And notice, of course, we do get that same number. All right, so we are ready for the second part of our conclusion here. So conclusion number 2, after I write in my yeses, yes there, and yes there. Okay, so now very simply we just have a different value potentially than 1 in the numerator. So here's how I have it on my sheet. So m over n. So again, there's our rational exponent, and its equivalency to radicals, as we saw, is the denominator would be the root, just like we saw in the first part. And now the numerator we see is the value that the base is going to be raised to. So something along those lines right there. And I also have it just kind of written to emphasize that piece. So now we know in the rational exponent, the denominator represents the root of the base, and the numerator represents what it's raised to. So something along those lines right there. Maybe you can get it to look a little nicer than what I have. Okay. So example 1, very simply, is just meant to solidify this idea a little bit, just going from one to the other and seeing the comparisons between the two. So let me read it in a little more formal way, and then we'll go through A through E. So example 1, convert to radical or exponential form. So obviously you can see A, B, and C are in radical form right now. We'll convert that to exponential form. And then D and E, as you can see, are in exponential form, and we'll just convert that to radical. So being able to see it in both forms, certain problems we might want to go ahead and gravitate towards radical form, others to exponential, so a little fluency with both of them would be great. Awesome, so we've got the square root, or the second root of 15. And by the way, if you want to go through these a little quicker than I am right here, by all means. But I think I'm just going to use this conclusion. Square root, now we know for sure, is the base raised to the 1/2 power. Square root of 15 is the same as 15 raised to the 1/2. So denominator is the root of the fractional exponent. And obviously in this case, you see the 30 is just being raised to the first. So, cube root of 30 is equivalent to saying 30 raised to the 1/3. This one over here, obviously I've got my raised to and I've got my root. So with the base 7, it looks like it's raised to the 3/4 then. All right, good. So A, B, and C just going radical to exponential. Hopefully that was a pretty seamless process. Now let's go ahead and reverse it and just go exponential to radical. And so in this case, remember, denominator is the root, numerator is what it's raised to. So it looks like cube root of 22 squared. Now just so you know, there's no real necessity in the order in which you do this. I could read this as the cube root of 22 squared, or if I really wanted to, I could think of it as the cube root. Well, in this case, I would do the square first and then cube root it, or I could take the cube root first and then square it. So I guess the moral of the story there is either way works, and we'll see a problem in just a moment or two where we might want to think about it in terms of one way as opposed to the other. Okay, and then this right here, this is what you typically would see this as, so 6th root 2 to the 11th. If you really wanted to, you could write it as the 6th root of 2 and then raised to the 11th. All right, again, hopefully able to go back and forth and see that pretty easily, because now let's jump it up a little bit in terms of the level. Let's get into example 2 first, and then we'll get into some more complicated expressions in example 3. All right, example 2, everybody. So simplify each expression without a calculator. So now just being able to see, well, what do these particular expressions mean, and then evaluate them. Well, what number is it actually equivalent to? So when I do 9 raised to the negative 1/2 power, as I'm looking at part A, well, the first thing that really jumps out at me right away, of course, is the negative exponent. And we have some expertise dealing with negative exponents and writing them in a way that's more meaningful. So to write it with a positive exponent, I would just bring it down to the numerator, or denominator, excuse me. But I've got 1 over 9 raised to the 1/2 power. And, well, what does that mean exactly? So 9 raised to the 1/2 power, as we saw, is really just square root of 9 in the denominator. And so as a result, without a whole lot of issue, it looks like 1/3 would be the answer. Now I'm going to box that up. And then I am going to grab the calculator and at least just simplify this one on there and see if we do get the right answer. Okay, so, all right, so perfect. Got that right there. And I'm going to go ahead and just type in 9 raised. And again, I need parentheses on that to the -1/2. And then just enter. And as you can see, it's 1/3. Awesome. Okay, so it'd be great if you could try these on your own as you're listening to my explanations. But 16 raised to the 3/2 power. Well, again, the denominator is the root. The numerator is what I'd raise it to. If I'm going to do this without a calculator, I guess I would ask you this. Which would probably be easier mentally? Is it easier to take 16 and raise it to the 3rd power? Or is it easier to take the square root of 16? And I hope you would agree, I think breaking the number down and making it smaller is certainly quite a bit easier than building that number up to a pretty large one. So I would say, for our purposes, we probably want to do the square root of 16 first, make that number a little smaller, and then raise that to the 3rd power. It just seems more logical, rather than trying to do 16 to the 3rd in our heads and then square root of that. So I hope you understand that process, and then obviously in this case, square root of 16 is just 4, so now 4 raised to the 3rd is just going to give us 64. Very nice. I'm going to jump right into letter C, and same premise, but again, the first thing I see is that negative exponent, so before I even think about the 2 and the 3, I do want to reconcile the fact that we want to bring that down to make it positive. So it's 1/27 raised to the 2/3. That looks great. And then the way I think about this is it's easier to go ahead and do the cube root of 27 than it is to do 27 to the 2nd power and then try to do a cube root on that. So long story short, I'm thinking we want to do cube root of 27 first, then raise that to the 2nd power. And so as a result, cube root of 27 would just be 3. So it's now we change that base from 27 to 3 by taking the root. And now we apply the raising to the 2nd power. Should be equal to 1/9. All right. So again, just some good mental math and really seeing what these fractional exponents represent and to evaluate them and getting these numbers right here. So 1/3, 64, and 1/9. Okay. Let's get right into example 3. You have definitely seen these expressions before, and so now we're just going to apply some of the conclusions that we've drawn so far to go ahead and simplify these, but we're going to use the same process that we've seen, so not too bad. Looks like A and B are in exponential form, and then C and D in radical form, but we might just sort of go back and forth there depending on what the problem suggests. Well, let's go ahead and try A first and foremost. And so if I was to give you this, at the very beginning of the year, without these fractional exponents, you probably would go ahead and think to yourself, well, how do I simplify? You might want to deal with the parentheses first and raise that to this power right here. And so, I think simplifying the parentheses makes the difference here. So I'm going to go ahead and take x to the 2/3 times y to the 1st. And then I'm going to go ahead and try to take x to the -2nd raised to the 1/2 power. So if you remember this is what's called power to a power property. And what do we do to those exponents when this happens? Well, if you remember, we multiply them. So -2 times 1/2. And -2 times 1/2 is -1. So that's actually x to the -1st when I apply that exponent on the outside here. And then here, obviously, it's what's called product raised to a power, so I do have to take the y raised to the 1/2. And of course, I do that, and I can remove those parentheses. Okay, so let's see what your addition and subtraction is like with fractions here, because I'm going to go ahead and multiply x to the 2/3 times x to the -1st. and then I'm going to multiply y to the first, times y to the 1/2, and multiplying two powers with the same base, we add the exponents, so we keep the base and we add the exponents. So 2/3 plus -1. See if you can pull that off in your head before I give you the explanation. So again, 2/3 plus -1. Well, of course, remember, to add fractions together, we need a common denominator. So I think of this as 2/3 plus -3/3. So 2/3 plus -3/3 would be -1/3. So it's x to the -1/3. And then same thing here. So I'm going to keep my base y, but I'm going to add the exponents. So I think of this as 2/2 plus 1/2. And 2/2 plus 1/2 gives us 3/2. So really super close at this stage. Just always keep in mind we do want to write these with positive exponents only to represent it in a more meaningful manner. And so in this particular case, I have this base raised to the -1/3 power. And so I'm hoping you would go ahead and take that, bring it on down. And so it's y to the 3/2 over x to the 1/3. All right. Looks really good. Okay, onward. Letter B. Couple ways to do this one. Let me throw a strategy or two at you, and then you decide what you want to do, maybe working ahead of me a touch. So we can either take all of these and raise it to the 1/2 power and remove the parentheses, similarly to letter A. I think that's what we did. Or we can simplify within the parentheses first, then take it to the 1/2 power. Now, again, there's no right or wrong answer here. I typically gravitate towards the latter, meaning I'm going to go ahead and simplify what's inside the parentheses first, then apply the exponent of 1/2. So, in order to do that, doesn't look like I can do anything with the 9 there, so the 9 is going to stay as is. But I am going to go ahead and divide the powers of x. So I have x squared divided by x to the 1/3. And just remember, of course, dividing powers in the same base, we subtract the exponents. So think of this as 2 minus 1/3, or just thinking about it in terms of common denominator, 6/3 minus 1/3. And so I'm getting x to the 5/3 there. So 9, and then x to the 5/3. And then let's do the same thing with the base y. If it helps you, put a little 1 in there. If not, no big deal. But basically, same thing. I'm going to have to take 1/3 minus 1, or 1/3 minus 3/3. And if I do that, 1/3 minus 3/3, I get to the -2/3. Okay. Now that's all great. So that's simplified within the parentheses. So I do have to apply my parentheses and, of course, raise that to the 1/2 power. Very, very nice. And now this is what's called product raised to that power. So I need to take each of these terms, the 9, the x to the 5/3, and the y to the -2/3, and raise that all to the 1/2. So 9 to the 1/2, in fact, we see it right here. 9 to the 1/2 is the same as square root of 9, which is just 3. Hope you remember that. And then x to the 5/3 raised to the 1/2, meaning I multiply fractions. So let's multiply the numerators, 5 times 1. Let's multiply the denominators, 3 times 2. So 5 times 1 is 5, 3 times 2, oops, sorry, hang on one sec, I forgot my base. Let's do that. There we go. So it's 3x to the 5, and then 3 times 2 is 6. There we go. I like that much better. And then same thing with the base y. This time I won't forget. And, you know, I've got the same idea. I can probably cross-cancel those 2's if you really want to. That's not a bad idea. But I can think of this as -2 times 1 in the numerator, 3 times 2 in the denominator, so -2, 6, or really just -1/3. Okay, it's really looking nice. I think we probably want to just go ahead and simplify the y to the -1/3, and I think we have it. So 3x to the 5/6 over y to the +1/3 box it up, and we are on to letter C. Okay. Well, letter C, cube root of 2 times fourth root of 2. So we've worked with radicals, of course, and if these were the same, if these were both cube roots or both fourth roots, we wouldn't even think twice about this. Product property with roots, you'd go ahead and multiply them, end of story. But we haven't seen one where this is a cube root and this is a fourth root. And I don't think we have a property in radical form that allows us to make this happen. So rather than just crossing it out and saying, hey, it can't happen, let's see what it would look like in its other form and see if anything jumps out at us. So what I'm thinking is, let's write it in an exponential form. Cube root of 2 is really 2 raised to the 1/3. Fourth root of 2 is really 2 raised to the 1/4. And so by converting it to exponential form, all of a sudden something jumps out at us. Well, this is just multiplying 2 powers with the same base. I mean, both base 2. And how do I multiply powers with the same base? I add the exponents. Okay, so I'm going to do exactly that. So keep the base, of course, we always have. And doesn't matter what these exponents are, just remember our properties. Multiplying 2 powers with the same base, we keep the base, and then we add the exponents. Well, when we add these exponents, I probably do want to get a common denominator, 3 and 4. I think the least common multiple of 3 and 4 would be 12. So this would be 4/12. This would be 3/12. And when I add 4/12 and 3/12, I get 7/12. Now, look, this is a perfectly legitimate answer. It's all well and good. My thought just for this one as I was looking at it is the original problem was given in radical form. So, why not go ahead and write our answer in radical form? So in this case, 2 raised to the 7/12 would be equivalent to the 12th root of 2 to the 7th. Something like that. So you can see how we were able to manipulate this ever so slightly just by changing its form and then changing back again, and you see what it's equivalent to. All right, letter D. So same premise. First of all, I've got a cube root here, a square root here. In addition, I've got a base 4 and a base 2. Well, let's do something similar to part C. So first order of business, I kind of look at it as that's 4 to the 1/3. This is 2 to the 1/2. And there's not much that jumps out at me at that stage because I can't multiply these 2 together if they're different bases. But it sort of does beg the question, is there a way to write both of those bases in a uniform base? And I'm hoping you would agree that working with the 4 is probably a good way to go because I think of 4 as just 2 squared. So I'm going to write this out for you, what I have on my sheet. And I think of it like that. And that allows me to go ahead and write both of these values in base 2. And just applying some good old-fashioned power raised to a power here. So multiply these exponents. 2 times 1/3 is 2/3. So 2 to the 2/3 times 2 to the 1/2. And we could start to see some good things happening. I'm going to have to bring this on up. Hope you don't mind. Now I can multiply these 2 together without a whole lot of issue. I do keep the base, and I do add those exponents. What do you think? Least common multiple of 3 and 2? Looking to be 6. So this would be 4/6, and this would be 3/6, 4/6, and 3/6. Got it. Cool. And again, it's perfectly legitimate. Given in radical form, let's go ahead and answer in radical form. So this would be the 6th root of 2 to the 7th. Wonderful. All right, so some good simplifying of some complicated expressions. So with this piece, we get into really the last big part of this lesson. And these expressions are going to get even more complicated at this stage. But let's see if we can work through it and develop a nice process so it makes pretty good sense for you. So it looks like at the bottom of your page here, I see factoring involving fractional and negative exponents. So we've done obviously lots of factoring. Now the values that we're going to see that we're going to try to work with in terms of factoring are going to get a little more complicated to work with, but if we keep the process in mind, I think it should be okay. Okay, so here's what I have on my sheet for this. So it's all going to be GCF, just so you know. So no real new pattern per se, but all greatest common factor on some more complicated expressions. So here's a conclusion to be drawn, and you feel free to ask about this individually if you're wondering why the conclusion really works. But I would say that the GCF of any powers in the same base, and we're going to see lots of these powers in the same base. So I've got this right here. So again, GCF of any powers in the same base, very simply, let's see what happened there. There we go. Sorry about that. Let's see if it works this time. Is the one with the smallest exponent. And I think I'll give you a quick example off to the side here just so it makes pretty good sense. And you can get really concrete with this if you'd like, or if you'd like me to get concrete in clarifying this concept, you just let me know. But again, the GCF of any powers in the same base is the one with the smallest exponent. So very simply, an example of this, and I'll erase this momentarily just so it doesn't get in our way, but if I gave you these two powers in the same base, and I said, what is the greatest common factor of x squared and x to the third? The GCF would be x squared. It's the smallest of the two. If I had these two, and again, I'll be super fast with this. If I had y to the fifth and y to the seventh, and I said to you, what is the greatest common factor of those two values? You would say it's the smaller of the two. It's y to the fifth. So keep that in mind, because we're going to start to see some really heavy-duty fractional exponents there, negatives and positives and the like. And just remember this conclusion. The GCF of any powers in the same base is the one with the smallest exponent. All right? Well, with that said, let's kind of build up here. Example 4 leads into example 5. So just piece by piece. So example 4, determine the greatest common factor of each pair of terms. And so because we're just talking greatest common factor, I'm going to very simply circle the 2. Maybe on your sheet, just do it very lightly. And we're just going to think about, well, what's common to both of those terms that I circled? Well, I look at the numbers, 16 and 24. Greatest common factor of 16 and 24 is 8. So I'm going to factor out that 8 when the time is right. And then I think about, well, x to the 3/2 and x to the 1/2. Again, a little more difficult with these fractional exponents, but if I keep that conclusion that we just put in mind, then it's not too bad. It's just the smaller of the two. So same base, greatest common factor is the smaller of the two. So the GCF here would be 8x to the 1/2. Cool. All right, letter B. Circle the 2 if you would. Very lightly on yours. I don't have that capability on my screen here, but circle it very lightly. And notice I have 2 powers in the same base. The base is x plus 1, so if I'm looking for the greatest common factor, I know it's going to be something in that base. And very simply, if I've got 1 raised to the negative 2/3, 1 raised to the positive 1/3, the greatest common factor is the smaller of the two. Negative 2/3 obviously is going to be smaller than positive 1/3. Okay. Now, that allows us to get into example 5, factor each expression. Write your answers with positive exponents only. So there's an A, B, and C here. Let's see if we can do this. This is some good math right here. All right, so I'm not going to really circle these because it really gets in my way visually, but 2 terms separated by the minus, and I want us to think about what is the greatest common factor. When we do that, guys, in fact, I'm going to write this just off to the side. Make a little note for yourself as well. It is very simply just GCF. And I'm going to try to find a very concrete way to explain it to you once we take out the GCF. So bear with me on that piece if you would. All right, so let's start it out. I see these two terms. Each one has a constant or a coefficient in it, and if I factor out, looks like from 6 and 12, probably going to factor out the 6. Looks good. Now the nice thing is this piece I don't have to labor too much here in terms of brain power because I have x to the 3/4 in this one, I have x to the 1/4 in that one. The greatest common factor is just the smaller of the two. So 6x to the 1/4 is what I'm going to pull out. And now everybody, here's the key. I want to go ahead and think about what's in the parentheses after I go ahead and take out the greatest common factor. Now here's how I do it. I work just left to right, and then I ask myself, did I take some or all of this term? And if I took some of it, that means there's some more left inside the parentheses. If there's all of it taken out, well then there's nothing left from that factor inside the parentheses. So, here's what I mean. Did I take out some or all of the 6? Well, I took out all of it. So officially there's a factor of 1 inside, but I guess we don't need that just now. Okay, then I move to the next piece. I just work left to right. Did I take some or all of the x to the 3/4? Well, if you look, I took only some of it out because I only took out x to the 1/4, which is smaller than that, which means I still have some x's left inside the parentheses. Now, what is it that I want to raise this to? That's the key. If you can get this piece right here, then everything else is cake. So how do I get that piece? Well, think of it this way. X to the 4th times x to the something has to equal x to the 3/4. By the same token, x to the 3/4 divided by x to the 1/4 should tell me what this is right in here. So I'm dividing these two powers, and when I divide powers, I subtract the exponents. So long story short, 3/4 minus 1/4 is 2/4, or to the 1/2. And you can see, if I asked you to multiply this back out, we would of course get this. All right, minus. Now I keep just working left to right. Did I take some or all of the 12 out? Well, I took some of it out because I took a factor of 6 out. So I've got something left, and 6 times 2 would give me the 12. And then did I take some or all of the x to the 1/4 out? I took all of it out, so there are no more x's inside. Quick glance. Any negative exponents that I have to deal with? Nope. So I haven't been boxing up lately, but we worked hard on that one, so let's box that up. All right, next one. Letter B. X plus 3 to the negative 1/2 minus x plus 3 to the negative 3/2. And we want to go ahead and factor out the greatest common factor. So don't think too much about it, everybody. It's just the smaller of the two. So negative 3/2 would be smaller than the negative 1/2. So we pull it on out. All righty. Now let's see what we have left in there. So in this particular case, I look at this. Did I take some or all of the x plus 3 raised to the negative 1/2? Well, I only took some of it out because I took to the negative 3/2 out, which is smaller than this. So I still have x plus 3's inside. And so in this case, I have to decide, well, what's that raised to? So I'm actually going to go ahead and close that off for a second and think about what it is I have to raise that to. And I do negative 1/2 minus negative 3/2. Negative 1/2 minus negative 3/2 is actually positive 2/2. Awesome. And then I put my minus. And I ask myself, did I take some or all of the x plus 3 to the negative 3/2? And I took all of it out, so there are no more x plus 3's in there. But there is something I have to put in. So just remember when you factor, there is an implied factor of 1 just right there because this times 1 gives me that. Cool, let's just simplify. So x plus 3 to the negative 3/2. I hope you would agree that this is just x plus 3 to the first, or really just x plus 3. Okay. And if I simplify inside the parentheses, that's just x plus 2. Now I hope you did notice we have this factor out in front that has a negative exponent, so we've got to deal with that. X plus 3 to the 3/2. Great. Let's keep it rolling. Letter C, 2 terms, separated by that plus sign. Let's do GCF on this. So, I have a 2 and a 4. Let's take out the 2. I have an x and an x squared. Smaller one is x. Let's take it out. I have 3x plus 4 to the 2/3, 3x plus 4 to the negative 1/3. So greatest common factor, don't think too much about it. It's just the smaller of the 2. Awesome. So that is our GCF. Now, I make my parentheses, and I'm going to see what the heck is left inside. So I hope you don't mind me doing that sum or all trick as I go left to right. I think it works really nicely. So did I take sum or all of the 2? I took it all out. Did I take sum or all of the x? I took all of it out. Did I take sum or all of the 3x plus 4 to the 2/3? Well, I only took some of it out because I only took out to the negative 1/3. So as soon as I say that, then I know I have some 3x plus 4s remaining. So I'm going to write that in there. What is it raised to? I do 2/3 minus negative 1/3. 2/3 minus negative 1/3 is 3/3. Cool. Working left to right, there's my plus. Did I take some or all of the 4? I only took some of it out. Did I take some or all of the x squared? Took some of them out. Still have an x in there. Did I take some or all of the 3x plus 4 to the negative 1/3? I took them all out. There it is. So nothing left there. Cool. Let's play cleanup. I have the 2x. This guy is going to go to the bottom, of course. Has to go to the denominator. Now, if you notice, again, anytime I get something like this raised to the first, then it's just 3x plus 4. So I hope you don't mind me doing a couple steps into one here, but this is 3x plus 4 plus 2x, because this goes away because it's just raised to the first. So, long story short, again, it's 5x plus 4. And then over 3x plus 4 to the 1/3. All right, that's how it works. Really, really nice. Now let's go get into the last couple. So here's what I have on your sheet where it says simplifying expressions with rational exponents. You can see these are really complicated expressions. But I have write the numerator, and you'll have to excuse my shorthand here, and or the denominator. It just kind of depends on what it looks like. So write the numerator and or denominator in factored form. So this is the a natural extension of the previous example. So factored form, and then just use exponential properties. So again, excuse my shorthand on that, to simplify further. Okay. Well, let's give it a try. So example 6. Simplify each expression. Write your answers with positive exponents only, but of course. Now I'm going to do part A in some good detail there, and I'm going to do part B as well. But if you feel like you get the hang of this after part A, that's fine. Don't feel obligated to continue with part B. But these are pretty complicated, so you might want to get just a redundancy on that part B, making sure it clicks. All right, so here's how it plays, everybody. It's the numerator here. Look how amazingly complicated that is. So what we're going to do is try to factor the numerator. So that's what I'm going to write off to the side. Factor the numerator. Very much like the last example. So if I look at this, I have this term minus that term. And so in terms of factoring, I'm going to look for the GCF. So think about that. I've got some x squared plus 4s in there. So I think from my perspective, I'm going to take out x squared plus 4 to the negative 1/2. Excellent. When I do that, I make my parentheses, and I'm going to see what's left. The only big difference here, of course, is I have another x squared plus 4 in the denominator. All right. So let's see what's going on with this. Again, just working left to right. Did I take out some or all of the x squared plus 4s here? Well, I only took out some of it because I only took out to the negative 1/2. So I have x squared plus 4s in there. Perfect. And that would be raised to the, let's see, 1/2 minus negative 1/2. So 1/2 minus negative 1/2 is really just 1. Okay, or I wrote it in halves. And then I didn't take anything out with the x squared, so there's still an x squared in there. And did I take some or all of the x squared plus 4 to the negative 1/2? I took all of it out, so there's none of this left on this side here. All right, guys, now let's just clean up. I see that, so another x squared plus 4, because now everything is multiplication and division. So notice right here, everybody, I have some division. And how do I divide powers with the same base? I subtract them. So what I see is x squared plus 4, and then subtract the exponents. Negative 1/2 minus 1 is negative 3/2. And then times, I have an x squared plus 4. Again, this can go away. So x squared plus 4 minus x squared. If I'm going too fast for you on this one, just check in with me. But actually, in this one, you just get 4. Because the x squareds would cancel. X squared minus x squared is 0. Perfect. Only one more thing to do. X squared plus 4 to the 3/2. Cool. All right. So again, I went through that, hopefully pretty well there. And but if it went too quickly for you, let me know. And again, let's try letter B. All right, same deal, everybody. Factor the numerator. Got that one, and then have this one. So what is the greatest common factor? Well, I have a 2 here, but only a 1 here. I have an x here and an x cubed here, so I'm going to pull out an x. I have a 1 minus x squared to the 1/3, 1 minus x squared to the negative 2/3. I'm hoping by now you really do get the hang of it, as that's the greatest common factor. Now we're going to play our sum or all trick on that. And let's see what's left. Did I take some or all of the 2? Well, actually, I didn't take any out of it, so I still have the 2. Did I take some or all of the x? Took all of it out. Did I take some or all of the 1 minus x squared to the 1/3? I took some, because I took to the negative 2/3. So it means I still have some in there. 1/3 minus negative 2/3 is just to the 3/3, which is to the first, which is just 1 minus x squared. So now I'm just going to leave it like that. Plus, did I take some or all of the x cubed out? Well, I took some of it out. I took an x out, so it looks like I still have an x squared. Did I take some or all of this one out? I took all of it out. There it is. Cool. Over 1 minus x squared to the 2/3. All righty, everybody, let's play a little cleanup on this. Can I divide these powers with the same base? You bet I can, because now everything is just products. It's just product and quotient. So let's go ahead and apply. So the x is fine where it is. When I divide these two powers with the same base, I subtract the exponents, and I get 1 minus x squared to the negative 4/3. And then when I distribute, I'm going to go ahead and draw those arrows in for you. I get 2 minus 2x squared plus 1x squared. So 2 minus 2x squared plus 1x squared is really 2 minus 1x squared. And then now, oh, I'm so close. Let's just bring the term with the negative exponent to the denominator. Got that. Everything needs to be accounted for, as always. Wow, that's amazing. How cool. So there are a few problems in the practice that'll help you with this, but the process, keep in mind from these two examples. And if you have a particular question on, like, where'd you get this and where'd you get that, and just call me over at any time. Thanks for listening, everybody. Appreciate it.